All right. Good morning, everyone. Welcome to our lecture 8. So officially, we're close to being done with 1/3 of the quarter. Sorry, 1/3 of the course. So this is our second visualization lecture. We are going to start where we left off last time. So remember, we were talking about plotting. Oops, what happened here? Oh, this whole thing was blank the whole time. Okay, go ahead and get logged in. And you know the deal. And there's also all of these QR codes in each one of those slides. So scan it, get ready to go. All right, wonderful. So visualization 2, we're going to talk about plotting distributions a little bit more. We're going to talk about how we can plot the relationship between multiple different variables. We're going to take a look at how we can make sure that we do transformation in a way that the plot that we're creating is going to be informative for the modeling piece that we're going to do after visualization. Remember, the whole point of doing visualization is that it's also part of our exploratory data analysis. So we need to make sure that we're comfortable with the scale that our data is in so that we can move forward with, say, the first thing that we'll do next week is going to be, not next week, like 2 lectures or 3 lectures from now is going to be linear regression. So we will investigate whether we are ready and our data is in a scale that we can do visualization, that we can do linear regression or not. And then at the end of today's lecture, there is kind of an information generally on visualization theory. So we're going to quickly go over some concepts that you have to remember about information channel and how to utilize information channel more effectively. So this is where we are. You're familiar with this plot, second visualization lecture. You know where visualization is going to become handy. It's in the EDA piece, and there's also the second purpose is for reporting as well. So let's dive into kernel density estimation, the topic that I started talking about, the motivation behind it in the previous lecture, but now we're going to talk about what it is exactly. So remember when I was talking about histograms, I was creating these histograms and I was telling you that, okay, there is a way that we can kind of define some concept of mode in our histogram. And then you saw that depending on the number of bins that we have, the mode that we will observe in the histogram is going to change. And then we said that we're going to use some smoothing function using a probability distribution kind of concept that removes all of those details, but generally captures the trend in the data. So what we're going to do today is we're going to think about a technique, and we'll learn a technique that will do that for us. And what is that technique? Think about having a histogram, and you're basically throwing like a string on top, and this string is going to take the format or the shape of this entire histogram, but without depending on a lot of those details that you see in all of those bars that we have in the histogram. How do we do this? We are going to use a probabilistic kind of approach in this case. We're saying that in order for me to figure out at any given point, what is the probability for me to be able to have a given data point at that specific value, we can define it using a probability function, as opposed to just directly counting the exact number of values that we have in our data set and then normalizing the height of these bars so that the area of all of those bars together do add up to be equal to 100% or be equal to 1. What I'm going to do is I'm going to say that I'm going to basically design a probabilistic approach so that once I'm looking at every given data point and I look at the projection of that data point, for example, to my kernel density estimate curve, I will be able to just roughly tell you what is the probability that I have a data point at that specific point, as opposed to just directly looking at what is the proportion in our data set. So how do we do this exactly? We will use a 3-step approach. And this 3-step approach basically assumes that the way that we're going to define this probability distribution function is that we will assume that for every given data point, there is a probability assigned for me to be able to sample that data point again. And we're going to define this randomness by a concept that's called kernel. So think about me having one of the data points in my data set. Say that, for example, that data point is HIV rate at the value being equal to 20. And what I'll do is I'll say that what is the probability of me coming back the next time and sampling one more time from my entire data set or from a distribution and be able to extract the same exact data point, right? So what I would say is that it is more likely for me to be able to capture this same data point. You'll see that there is a high probability here at the center of this curve. And for those who have taken probability or statistics courses, you know that this is a Gaussian curve or bell curve or a normal distribution that you've seen before, with the center or with the mean being at that exact data point that I have. And as I move away from that center, the probability is going to drop. What that means is that if I want to come back and sample a data point, with high probability, I'll get the same data point. With the smaller probability, I'll get a slightly higher value or a slightly lower value. And as I move away from that center, the probability is going to drop substantially. That's why it's kind of modeled with this Gaussian curve that we have here. So this whole idea is kernel, but this is only for one data point, right? How can I design a probability distribution function for my entire data set? Because remember, the goal was to go back and be able to just have a probability distribution function for the entire data set so that we have a summary of everything that's happening in the histogram generally. So what I can do is technically, again, a three-step process. The first thing is that I'm going to assume that there is some randomness assigned to each given data point. And I'm going to capture that randomness with this kernel that you see right here. There are different properties for this kernel. For example, this kernel can be wide or can be very narrow, depending on the bandwidth or standard deviation that we're defining for this Gaussian. The default value that is being used in Seaborn is equal to 1. So technically, standard deviation is going to be set to be equal to 1. But like if you want to have a flat curve or a wider curve, you can have a standard deviation or that parameter to be a larger value or can be a smaller value, and you have a very sharp peak in that case. I'm technically saying that I'm going to more constrain my model or my data set to give me exactly the same data point. And I'm going to just have a very sharp peak there. And if you give me a data point that's a little bit different, then I'm going to give you a very low probability of you being able to sample that data point that you might observe next. So what I'll do is I'll put this kernel on top of every given data point, because all of the data points, we're going to assume that there is some randomness assigned to all of them. And I'm going to show you how we do that with a three-step process. The first step is, again, putting a kernel on top of every given data point. So I'm going to show you an example with only 5 data points for simplicity for now. We're not going to look at the entire data set. And I'm going to say that, okay, for these 5 data points, I'm going to visualize them using something that's called ROC plot. ROC plot is going to give you just some indicators at that exact kind of location. So for example, here I'm saying that, okay, I have a bunch of different points. Go ahead and put ROC indications or those indicators with the height of 0.1 at every given location that we have here. So these are 5 data points that I have, right? That's a ROC plot. That's my data set. What I'm going to do is I'm going to say that each one of them, there is randomness associated to each one. So let me go ahead and put a kernel on top of each one of them. So this is the first step. So thinking about this, smoothing this probability so that I'm not really saying that either this data set or nothing, or this data point or nothing, but I'm going to say that there is a probability. It's more likely that you're going to give me that data, but it's also I'm going to be a little bit flexible and accept a slightly smaller value or a slightly higher value than the data points that we have in our data set. This is just kind of simplifying assumptions that we're making so that we can make a probability distribution function. Okay. I kept saying that I want to have a probability distribution function, right? Meaning that when I look at all of these probability functions that I put on all of my data points, and I look at them in aggregate, so I sum up all of these curves together, I want the area under the curve to be equal to 1, or the integration of this function to be equal to 1. But right now, what you know from each one of these kernels is that the area under the curve of individual one of them is equal to 1. So if I sum up all of these, I'll get a value of 5, right? So I need to scale things down. And the scaling technically means that the probability of me being concerned with every given data point is 1/5 of the entire data set, because I have 5 data points, right? So there's a probability that I'm concerned with this specific data point, and if I want, and that probability is 1/5. But then looking at that, what is the probability that I get exactly the same value or a slightly higher value or a slightly lower value? So that's why each one of those curves need to be scaled by a factor of 1/5, so that we basically have a proportional kind of probability assigned to every given data point. If I had n different data points, the scaling factor should have been 1/n, right? And then therefore I have a bunch of different small curves with the area under them being 1/n, so that later on I can sum them up together. N curves with the area under the curve of 1/n is going to give me the total area under the curve of 1, which is what we're going to do in the third step. In the third step, we said that, okay, I modeled each one of those individual data points, but let me go ahead and aggregate all of them so that I see how these data points that are clustered together or closer together are going to influence each other. And then I have a higher probability for those range values, and then I have lower probabilities for the ranges that are outside of the normal range that we have in our data set. And that's how we will get a kernel density estimate. This is a density function. The area under the curve is equal to 1. And then technically each data point that you have, then technically you can project it to this curve and then be able to find out what is the probability that you will be able to sample that data point, right? It's not really strict to the exact values that you have in the data. So going from the data that we had and then putting the kernel density estimate on top of the histogram, that's the plot that we'll get on the right-hand side. One thing that you might want to notice is there's like bumps at the points that we have those two bars, right? And the higher bar has a higher kind of peak right there. So this is kind of an indication that we are doing some kind of smoothing here. The other thing that you might want to notice is that the range of this function extends below the smallest value and above the highest value. And this is natural because the range of the, or the domain of the Gaussian function that we were applying to each one of those data points is just all of the x values. So that's why we have all of those kind of small probability values also extending in this area and also in this area. And this is the whole idea of kernel density estimation. It's just a smoothing function that we're putting on top of our data, and it's going to give us a probabilistic view of the distribution in our data, and then we can basically measure the general trend in the data without dealing with the outliers and noises that we might have in the data. So this is a very sophisticated kind of function putting together all of those 3 steps. What did I do? What I did was I put a kernel on top of each one of my data points. If you take a look at, for example, this function right here, or this blue curve that I have, this is a kernel, right? What is that kernel? That kernel says that I have a bandwidth or an alpha parameter of 1, meaning that the width of this kernel is going to have a standard deviation of 1. So I'm not going to have a wide kernel, or I'm not going to have a narrow kernel. The standard deviation or the bandwidth is going to be equal to 1. That's what you're seeing as this subscript 1 being annotated on the K. K stands for the kernel that we're dealing with. And then I'm saying that for every x value across the x-axis, I'm going to basically define this Gaussian kernel centered at the value of 2, because that's where my data point was. In fact, if you take a look at where the center was, it was, I think, around 2.1, but for simplicity, I put it here as 2. And that's how each one of those kernels are defined. That's what you're seeing in this equation right here. It says that, okay, go ahead and put a kernel. We're assuming in this case that the kernel is the Gaussian kernel. It's parameterized by alpha, and alpha is the decision that you're making ahead of time. This is the bandwidth parameter, and then I'm saying that this function has 2 has two kind of arguments. One of them is fixed because you're basically fixing this Gaussian kernel at each one of those xi values, and xi's are your data points, exactly the data points that you have in your data set. And then you're saying that for every given x value across the x-axis, I should be able to calculate the probability value or the probability that this kernel is giving me. What do I do next? The next step is that I need to scale all of these kernels by a factor of 1/n because I have n different data points. The probability of me being concerned with one of them is 1/n. And then I'll go ahead and sum up all of these values together so that together I'll have that nice final curve that is kind of an aggregation of everything that we talked about. But notice that this function is a function that I say takes in a parameter or decides about this parameter that we call it as a hyperparameter. We're going to talk about what hyperparameter means in 4 weeks-ish, but just know that this is something that we're going to decide ahead of time. In this example, I said alpha is equal to 1. That's the width of the kernel. And then I'm saying that for every given data point, for all of the values across the x-axis, I know my xi values, I know my alpha, everything is known. So I'll just put this value into the equation, and then I should be able to get a probability value. And that's what a kernel density estimation function is about. Let's now talk a little bit more about this kernel. A kernel is nothing but a probability density function. What is a probability density function? It just needs to be defined for all values of x. And then for all values of x, the output should be non-negative. So the probability density function should be greater than or equal to 0. And that the area under the curve should be equal to 1. Or if you integrate the function, it should integrate to 1. That's what we had with Gaussian kernel. This is the equation for Gaussian kernel. For those who have not seen it in a probability or a stats course, I don't want you to know the details. Just look at the equation and make sense of why this shape is this bell curve shape. It is centered at xi because when x is equal to xi, that's the time that the numerator is equal to 0, and we have the maximum probability. That's why it's centered at xi, this kernel. And then you're also seeing that the width of the kernel is controlled by this alpha parameter in this equation. And that's how you can make sense of why by increasing alpha, the width is going to increase, and the probability is going to, the rate of the decrease of the probability as you move away from the center is going to decrease if your curve is wider compared to when it's a little bit of a sharper curve. And everything else you kind of visually can make sense of and know what a kernel is and how we're using kernels in kernel density estimation. So you might be asking me that why did I keep talking about Gaussian kernel? Mostly because Seaborn implements only Gaussian kernel as the backbone of the kernel density estimate plot or KDE plot. It used to have other types of kernels that you could basically, as long as you would satisfy those conditions for the kernel, you could use them, but it's no longer the case. And mostly it's going, not mostly, it's going to use Gaussian kernel in the backend. I talked a little bit about the bandwidth or this alpha parameter. I said that if alpha is small, we're going to have a spike here, kind of Gaussians, and that's exactly what's happening here. So think about this data set. What you're seeing very kind of tiny here is the log plot. So I have those logs and indications for each one of the data points, but then you can kind of see that where I have a high density of those log kind of markers, then I have also a very kind of tall bin for that histogram. So if I were to go ahead and put a bunch of these spiky curves like really next to each other, and I scale all of them, and I sum up all of them, it's going to look something like this. And it's going to be very spiky because those data points are going to be a little bit kind of distant from each other as you move away from that center of the distribution. So that's why you're going to see a lot of like independent spikes in kind of a less populated kind of range of X. This is an example that alpha was set to 0.1. If alpha is equal to 1, you'll see that all of those noises that unnecessarily that I added, now they're gone, and you can kind of make sense of why that kernel density estimate is kind of an estimation of what you also see in the histogram. But if you keep increasing the alpha value to alpha equal to 2 and alpha equal to 10, all of those small details are going to be washed out, and you're just going to be able to get the sense of the general trend in the data. So this very high alpha is also not super ideal because we're not going to be able to extract the details that are necessary for us to understand a little bit just more than where the peak of the data is, right? So that's why picking alpha is going to be a hyperparameter that's going to be a little bit tricky. So you might want to try different alpha values and then figure out which one of them captures the general trend of the data a little bit better. Kind of think about the case that with histograms, we were also changing the number of bins so that like we see at what point we have the general trend kind of figured out. This is kind of also the same. And if you think about it a little bit deeply, you can make sense of why bin sizes can correspond to the different alpha values or these bandwidth values that we have. So I promised to show you another type of kernel. I said Gaussian kernel is what we're using, but we're not generally with the kernel density estimate, we're not bound to always use Gaussian kernel. Anything that is a kernel and fits to the criteria of being a probability distribution or probability density function we can use. And one example is boxcar, which is nothing but like a plot that you would see as like a box and the alpha that you can decide. And then the alpha is going to basically say that put a box around xi with the width of alpha, and then also the height is going to be 1 over alpha because the area under this entire box is going to be equal to 1. So here is going to be alpha, and then also here the height is 1 over alpha, and the area again is going to be equal to 1, obviously. If I try this boxcar kernel on top of the same data set that we had, I'll see that weirdly looking kind of plot that you might think that this resembles the histogram that we had. It looks like it, but it's not exactly the same. But again, it might be a little bit similar. In practice, we never use it. And we're just showing it to you that you know that the general idea is just to put this kernel on top of the data points, scale them, sum them up, then you have a probability distribution for the entire data set that you have. Okay. So now think about this slider question for you. Which one of these following plots, A, B, C, D, are a valid kernel density plot? There is a very good question. For those who are familiar with signal processing, the idea of kernel is similar to convolution. But if the term convolution doesn't ring a bell, ignore it. Okay, let's see. What do we got? AC. Yeah, you get the correct responses on the chart. So A, C, and D should be the top ones. All right, right. The issue with B is that if you take a look at the area under the curve, the height is so high at 0.7 that the area under the curve visually you can inspect and see that that is greater than 1. For the rest of them, we guarantee that we generated them in a way that they are kernel density estimates. And you can visually kind of double check what's happening with the area and so on and so forth. Question? So what's a valid density plot? What's a valid kernel density plot? That's a good question. I think it depends on also your data. So if you know the distribution of the data, and like there is a density plot that doesn't have anything to do with that distribution, then technically they are different, but I didn't show you the original data. So your guess is basically that which one of them is a density plot. Yes, technically, that's correct. All right, wonderful. Moving on. Some plotting functions revisited. There is a nice this plot function in Seaborn from the Slido questions. Last time we kind of gathered that most of you are interested more about Seaborn. So Seaborn is a kind of a nicer implementation of Matplotlib that actually sits on top of Matplotlib, and that's why they really work well together. And it has also some functions that are wrappers of other functions within Seaborn as well. So for example, here you're seeing that I'm using this plot. This plot is a wrapper on top of a bunch of different plots, his plot, KDE plot, and ECDF plot that I'm going to tell you what that is. But technically what I can use is instead of calling his plot separately or calling KDE plot, which you can guess that it's going to create KDE plot for us, I would just directly say that, okay, I want to pass my data. I'm passing the attribute that I want to be plotted. And then I'm saying that the kind of the plot that I want to get out of you, because you are a wrapper on top of a bunch of functions, is to give me the hist plot. So it will automatically go ahead and call the histogram or the hist plot of Seaborn, and then it will give me the result in the output, which you're seeing that that's a histogram. Here I'm saying that the stat is equal to density because by default, the stat is equal to count. It's kind of a little bit counterintuitive, but technically, if you just want to look at the spread of the data, it doesn't matter if you're looking at the counts or the density values. But if you're really concerned with just knowing what's the probability density at each given data point, then technically you want to say that the stat or the scale on the y-axis be density. So let's see what the KDE version does. Changing the kind to be KDE, I'll see this nice KDE. The default alpha value here is equal to 1. There are examples in the demo code for today that you can change. You can scale the alpha or you can change the alpha directly, and then you'll be able to get different levels of details from the KDE plot. What is this ECDF plot? So kind equal to ECDF. ECDF is empirical cumulative distribution function. Starting from the smallest value up to the largest value, you'll basically have a cumulative probability function, which basically tells you what's the probability or the ratio of the data points that are small or less than or equal to that given data point. So if we are looking at the highest value right here, the corresponding probability here is equal to 1. So that's a cumulative distribution function that we see in the plot. Not probably super necessary, but for you to see that it's kind of a nice functionality to have, and you can easily use this plot instead of individually calling those other plots. So far what we've talked about was just visualizing distribution of one variable. What if I have multiple different variables? So in data8, you've seen that we show the relationship between two variables using a scatter plots, right? Remember these plots here that in data8 they were talking about, we're going to visualize everything and we're going to show you that correlation is not causation and compare correlation values and then see like whether that matches the intuition that we have with the visual that we see in a scatter plot. We are also going to use a similar kind of version of a scatter plots in data 100, specifically the notation that we're using in Matplotlib and Seaborn is that in Matplotlib we can say dot is scatter. And remember, the convention of Matplotlib was to get a sequence of values. So I'm getting a sequence of X values, sequence of Y values, and then I'll just go ahead and show you a scatter plot of X versus Y. So every marker is a pair of values that I'm visualizing. With Seaborn, we are calling a scatter plot function. And this function, again, the standard of Seaborn, getting the data, getting X and Y column labels. And then if you want to use color as the third channel, you can do that. We've seen this with hemisphere example in the previous lecture. This is where you can also throw in an additional kind of hue channels so that you can visualize a categorical value together with the two quantitative values that you're visualizing comparatively using a scatter plot. So this is what's going to happen if I go ahead and visualize two quantitative values here. And then I'm saying that use the hue to visualize the continent, which is the qualitative or categorical variable in this case. So you see that different continents are going to be visualized with different colors. So this is kind of a nice visualization. Again, showing the relationship between two variables, highlighting also a third variable. So the three things are being visualized here. One issue that we might have with the scatter plots, and mostly with the scatter plots, is overplotting. Overplotting is this example. So you see that I have a bunch of these data points really kind of clumped together in one area, and it's really hard for me to figure out, even if I was doing the color coding for different continents, to figure out, oh, how many countries from each continent do I have? Because they're just going to be plotted on top of each other. So making a distinction between them is generally not easy. So we have to get creative in terms of avoiding overplotting in a scatter plots. The simplest way that we can do is by adding a noise and using something that's called jittering. So what you're seeing in this case is that I'm creating two noise objects. So one for all of the X values and one for all of the Y values. And they have different ranges because my X and Y range is different. So here the range is between 0 and 100, and then X has a range of between -15 to like 10. So that's why the range of the noise is different. But the bottom line is that at the time that I want to plot, and I'm calling this a scatter plot, I'll say that I'm passing you the X, and then I'm adding the noise directly to X. And then I'm passing you Y, and then I'm directly adding all of those noise values that are corresponding, that correspond to each one of those Y values that I have. And then I'll be able to visualize them. So things are going to randomly spread a little bit. It's not going to be super accurate, but at least visually, you will see what's happening in your data, and points are not going to be really on top of each other. But there are also other ways that we can visualize relationships or visualize relationship between two variables so that we can get a higher level information and kind of also at the same time avoid the overplotting issue that we had. Starting from 2-3 lectures from now, we're going to talk about linear models. What we can do with Seaborn is I can say that I want a linear model on top of the scatter plot that you're showing me for visualizing the relationship between two variables. So I'm going to give you my data frame. I'm going to give you X and Y, and then give me all these scatter points. Give me the linear regression line, and also give me the confidence interval. We're going to play with this LM plot a little bit later, but you will see visually by this linear regression line whether like there is a linear relationship or not, or what's those confidence intervals and how you can interpret it, and then go back in the EDA cycle and then fix the relationship between these two variables so that you can do what you want to do with a linear regression model. You can also call joint plot. These are too many plots that I'm covering, but I promise you in the midterm and final exam, we're going to give you a reference sheet that has all of these functions and description of all of them. So as long as if you see joint plot, you know that it's going to plot something jointly related between two variables, you should be good. And also the syntax of Seaborn versus Matplotlib. But what does it do? It gets, again, the same thing, data frame, X and Y. And then what it does is that it's going to give you this histogram, also nice on the X and Y axis, which is going to show you the distribution across X and the distribution across Y. Why is it significant in this case? Because, for example, if I look at the distribution of Y and I see this high bar, I know that majority of the Y distribution should be in that specific range corresponding to that bar, right? So then I'll basically know that, okay, there is a lot of overplotting that's happening here, kind of visualizing or like kind of making sense of comparatively what's happening in that region versus the rest of the region, right? So this is one way that you can, in your mind, see or identify overplotting and also compare the distributions, obviously, that you can get. So one thing that I also want to make note of is, remember in the KDE plot, I had those markers in the rock plot and I was putting kernels on top of each one of them. What if I do the same thing in two-dimensional space? For every dot, I'll put a kernel, a 2D kernel on top, and then I'll scale everything, I'll sum up everything, so I have a 2D distribution, probability distribution over the entire data set. I can do that and I can visualize it in different ways. One way is to just say that, okay, I'm going to go ahead and say that I want to get a hex plot. So this is a joint kind of plotting, but at the center, I don't want to have those scatter points. Instead, I just want to summarize how many or what's the ratio of the data points that I have in each one of those hexagons that you see at the center. So the darker areas correspond to more concentration, the lighter areas correspond to less number of samples in those cases. So this is, again, a nice way of summarizing all of the overplotting that was happening in the plot. Or I can go crazy and say that, okay, give me that 2D KDE plot that you were promising me, right? What is this 2D KDE plot? This basically says that it's going to be this 2D probability density, probability distribution function, which technically is going to be darker in the areas that I have more points, and then lighter color in the areas that I have less number of points. And you see that it has color fill because I said that fill is equal to true. Otherwise, it would just give you those tiers that you can basically make sense of, those like edge colors, and then see what's happening and how the trend is changing in terms of the probability of different regions changing as X and Y changes. Okay? Really powerful stuff. This is the end of all of these kind of coding things that I wanted to show you. We're going to talk about more fun stuff, but before I move on to the second part, I also want to put it out there that there is a third library that we didn't cover, which is called Plotly. It's Python-based, using also JavaScript, which makes it really easy for you to interact or use it for kind of web applications. You probably have seen me using different plots that I would be able to hover over something and show you what value is in that location. We will periodically use Plotly in lecture, also in the labs and in assignments, because sometimes it's easier for you to be able to interact with the plot, be able to rotate the plot and see something in 3D when we move to 3D space and such. But it's not going to be super complicated. You just read the function, you'll know what it does, because now you know what categories of plotting generally we're using. Okay, moving on. Remember, we were talking about overplotting and the fact that overplotting is going to make visualization complicated, and we're not going to be able to understand what's happening in the underlying trend of the data. One way of avoiding overplotting is by transformation. And again, we use it because a lot of time it's easier for us when the data is in a proper format without any overplotting, that we can look at the trend, explain it for ourselves, or be able to show the trends to some human observer that was not part of our EDA, and then they will be able to just understand the pattern right away. So those patterns really have to be clear in our plot, and then there should not be any kind of overplotting happening. So this is a very bad example. So you see that I'm plotting two different things here. So I'm plotting gross national income per capita, and then I'm showing adult literacy rate. And you're seeing that there are two general issues with this data set. First of all, the data is really smooshed together, and I'm not going to be able to, for example, identify what's happening here. And there's no clear relationship between the X and Y that I can directly explain. There is no linear relationship, and then there should be a higher order relationship between X and Y, but it's really hard to debug or understand what that is exactly. So for these purposes, we might want to make sure that we transform our data to a format that can be easily understood, which is what we refer to as linearization. So linear relationships are the easiest kind of relationships that we can understand. So what we will do is we will go through a process of transformation that linearizes our data. So if I have, for example, GNI versus adult literacy rate, I will walk you through a transformation phase, and I'll show you why I do the transformations the way that I do, so that I am showing you now here log of GNI versus adult literacy rate to the power of 4. And now looking at these transformed scales, you can see a clear linear relationship between them. Again, why is linear relationship interesting? Because it's really easy to understand and explain. Now I can explain that if you increase X by this amount, Y is expected to be increased by this other amount. And also the fact that the first modeling algorithm that we're going to take a look next week is going to be linear regression. So we'll see why that's going to be very helpful. So let's see how we can do it. How can I linearize this specific data? And what do I mean by linearizing? What are the issues that I have to resolve so that I have a linear relationship between whatever axes that I have on axis values I have on X and whatever values that I'll have on Y? This is the first issue. The issue is that I have some outlier values or these large values on the X axis, right? Why is that the case? Why is that an issue? If I want to have a linear relationship between X and Y, if I wanted to go ahead and, for example, find this line that generally captures the trend for the rest of the data, it's not capturing so well, but like comparatively, then it's not going to have a good performance for those outlier values or those large values. So what I need to do is I need to make sure that most of the values on the X-axis are within the same scale. So I don't have super large values or super small values and bringing everything to a similar kind of distance to each other. The second issue we have is with all of these data points that are kind of clumped together in the left side, top left side of the plot. And the issue is that I have a lot of large Y values together that I can make a distinction between them, right? So as X changes, you're seeing that all of these Y values are still top here. So I don't know what's the significance of changing X in terms of how it would reflect in the change of the value of Y. So what we're going to do is we're going to take a look at these two pieces, and then we'll see how we can address each one of them individually. So let's address this issue first. So I said that I want to do a transformation. Obviously, I'll need to do a transformation on the X-axis that I want to proportionally bring all of the values comparatively close to each other. What kind of transformation do you think I can use? Yes. Sorry, I have a hard time hearing you at the. So the transformation that we need to do is on the X values. That's right. And we need to use the transformation function that technically is going to change large values more than changing smaller values. So we're going to use a transformation. So let me show you here. That is going to, for example, looking at this large distance, a transformation that shrinks this distance to some smaller value. But at the same time, when I'm looking at the distance between, for example, two values right here, I want these values to shrink or these distances to shrink, but I want them to be shrinking proportionally less. So everything is gonna basically going to reduce in value, but proportionally, I want to shrink large values more, which what we know from math is that log transformation is going to do that for us. I'll take a log of these values. Log of these large values is going to significantly reduce those values, and log of the small values is not going to change those values that much. That's why the scale is going to be a little bit closer to each other, right? So that fixes that issue. I have kind of a kind of uniform distribution of the data points across the X-axis. So I can directly say that, okay, there is this line or this linear relationship that I can define between X and Y. But it's still the issue of having these set of large values up here still exists. For a lot of these values, as I'm changing X, there's nothing happening with Y. But I need to be able to make a distinction between those Y values a little bit better. So I need to push them a little bit up. So this is kind of where we're going to look at the transformation of the Y-axis and also making sure that now we can push all of those high values of Y a little bit further. And then we're also pushing small values of Y a little bit, but to still be able to make a uniform kind of distribution across the Y-axis. So the transformation that we can use here is going to be the power transformation. So I would say that, okay, if I calculate Y to the power of 4 or whatever value that we're plotting on the Y to the power of 4, then technically all of those Y values that were clumped together, now their differences is going to be more clear and they're going to be spread out a little bit more. Still, I'm going to increase the small values of X as well. But then again, it's going to create a very uniform distribution across the entire Y-axis. So that's why you're seeing now this difference of this plot compared to what you saw here, that you're seeing that all of those values up there, now they're more spread out. Okay, why was it helpful? Because now that I did the log transformation of X and power transformation of Y, now my X dimension is technically log of X. My Y dimension is Y to the power of 4. From data 8, you know that I can fit a linear regression. Now that it is linearized, the whole purpose of transformation was linearization. So I'm linearizing. Now I can come up with a slope and intercept and then define this linear relationship. One thing that I might not be happy is like explaining things in terms of Y to the power of 4 might be difficult. So I can go ahead and do a reverse transformation and write this equation in terms of just Y. So I would say that Y is equal to whatever it was before to the power of 1 over 4. And then I'll be able to now visualize the exact trend of the data. Now I can explain what's happening. Otherwise, it would have been very hard for me to look at that distribution and then say that, okay, I'm expecting that the model is going to be this complex model to the power of 1 over 4. It would have been impossible. That's one of the reasons that we do visualization, that we do transformations, and also we use visualization at the same time to just visually take a look at the data and then see how it's spread and then make sense of what kind of transformation we need to do. Okay, how do we tell what kind of transformation we should do? Because it sounded like a magic that I was taking log or I was doing power transformation. We can use something that's called Tukey muscular bulge diagram, which all it is that it tells you that if your data bulges one way, you can use the transformations on the axis in that specific area and then be able to transform your data in a way that it linearizes itself. You're going to get this also in your reference sheet for the midterm, but you should be able to utilize it and use it in practice in problems and also in your homeworks and lab. So let's take a look at what happened with the example that I had. Remember that this was my data, right? If I'm generally looking at the trend of my data, this is how my data was kind of shaped, and it is kind of similar to this upper left area of this Tukey muscular bulge diagram. And you can see on the transformations, it's suggesting me that I can do Y transformation or I can do X transformation. You can do only one or you can choose to do both. But if you choose to do a transformation on the Y-axis, only one type of transformation you'll apply to that. So for example, here it's telling me that, okay, you can transform your Y-axis by taking it to the power of 2 or 3, and it gives you a sense that it should be a power transformation to correct what you want. So you can do power transformation, which is exactly what we did. So you can take one step, do power transformation, visualize your data, see if your data is linearized or not. If it was linearized, good. You don't need to do X transformation. If it wasn't, what was the issue with your X? In this specific criteria, I can kind of see that with log transformation or a square root of X, then I could have corrected the issue with the x-axis because of the shape of the data, right? All of those transformations are because of the shape of the data. And if you take a look at all those transformations and how the data might have been bulged to different directions, you'll make sense of why they're there. So that's why we use log. We use also power transformations. But notice that if I'm doing X transformation, I'll do one X transformation. If I do Y transformation, I'll do only one Y transformation. You don't need to have multiple Y transformations, right? There is one shot transformation that we do. And that in a lot of cases, one of X and Y should be enough. In that specific case that we saw, the data was so messy that I had to do two transformations. But most of the cases, one should be enough. All right, cool. How are we doing on a Slido? Sure, yeah. Good. Wonderful. So a lot of complex stuff we covered. Now we have half an hour of like informational session. Kind of thinking about, as you're thinking about creating a visualization, what goes into deciding what channels we want to use and how can we create the visualization in a way that uses all the informative channels of human perception more effectively. So let's take a look. We generally say that, again, all of these visualizations are for human, either part of your EDA or part of the reporting that you're doing. Here, I basically plotted the age distribution as well as the amount of fare that each individual paid for Titanic, right? So just looking at this visualization, this doesn't seem to be a very bad visualization because what I can gather from this is that there are some people around 40s who were very willing to pay these high fares, and there are some people on the older range of the age that were kind of, the number of those individuals were smaller and they paid a little bit less in fare for Titanic, right? This is just a summary of the data. I should be happy with it and I can move on. But how did we decide to make this kind of a scatter plot or show this relationship between X and Y using a scatter plot? And why we do that in the first place? If I wanted to see, for example, the maximum age or the maximum fare, I could just go and get some summary statistic from the data and just be done with it. This is a very nice example that you can see that there are 13 different data sets. They're all visualized here. All of them have the same X mean, Y mean, a standard deviation across X, a standard deviation across Y, and the correlation between X and Y, but they are different data sets, right? So that's why summary statistics are generally not enough, and that's why as part of our process, we always want to visualize our result and visualize our EDA as well. But let's now talk about how these visualizations are being created. So let's say that I had the data set of all of these individuals who bought a ticket for Titanic, and I have the age distribution of all of them. There are some null values, which is fine. But if I want to get a sense of what's happening generally in my data set, what's happening generally in the distribution, it's really hard to just look at all of those age values and make sense of what's happening, right? But instead, if I use something as simple as this rock plot right here, which shows me, it has one indicator per each one of those individuals, and then it placed at the right place. So for example, there are all of these individuals that are around like 37 to 40 years old, and there are multiple indicators, and where there is like a thicker kind of line, that means that there are more than one individual. And there are some areas like right here that there was no, for example, sample. So this immediately is going to be a better visualization for us as opposed to scrolling over the entire data set. We could have gone and used 2 dimensions because this is only utilizing 1 dimension, only utilizes the Y dimension. I could have utilized 2 dimensions, X and Y, and I could say that, okay, I'll put age on the X axis right here, and I'm going to give you a better summary as opposed to you visualizing, visually figuring out the distribution of the lines. I'm going to tell you that distribution, or I'm going to tell you density or the count. And then you'll be able to see what is the majority of the age ranges for those individuals and where are the tails and so on and so forth, right? So this is why visualization is important. and utilizing as much channel as possible in the plot is going to be very useful when you're summarizing your studies. So how did we create the ROC plots? We had the data set. For each one of those data points, we put a marker, right? The marker was those lines. And then the second step is to do encoding. So I would take each one of those markers and I would put it in the right place. Encoding was that, okay, if this marker is associated with the age 40, let me put it at this exact position that is associated with the age 40. And that's how one ROC plot came along. I could go and change the marker to like a circle. And notice here that the difference here compared to the previous case is that in the previous case, each one of those markers was kind of a one-dimensional marker. Like it was only marking one position, right? And because the plot was one-dimensional, it made sense. But if I go ahead and say that, okay, I'll change the marker to circle, and circle can represent a two-dimensional information because it takes a space on the x-axis and also it takes a space on the y-axis. And I do the same encoding that I did before, I'm going to get this plot, which is not going to be as informative because I can't look at those densities that those line markers was giving that were giving me. But then a better place that I could utilize these circles would be in a case that I'm visualizing a 2D information. This is how you're deciding between a scatter plot and you're deciding between the ROC plot. I have one thing to show. I can just show it with one-dimensional indicators using a ROC plot. I have two things to show. That's why everything that we have with the scatter plots are shown by kind of a two-dimensional markers that we have. So here we're visualizing age and fair. We have those markers, and the encoding, instead of only one-dimensional encoding, here is going to be encoding for age and for fair, and then we're going to put that dot somewhere on the plot, right? So think about this entire process that we have markers, and then we have different channels that we're putting those markers in those channels in an appropriate way. So this is a question for you. So going beyond 2 dimensions, we saw 1 dimension, we saw 2 dimension, but going beyond 2 dimension, looking at this plot, how many channels of information do you think is being used here? And this is a slide up for those who missed the first one. So the question is, looking at this plot, how many channels are being utilized? Because we might want to think about how many channels generally exist and what are the best ways that we can utilize all of these channels. That's why we're looking at this. So let's take a look. There are 4 channels here. And your majority response is correct. And all of those 4 is that we have encoding on the x-axis, we have encoding on the y-axis, we have encoding of color, and we have encoding of area, right? The area of all of these circles does encode something. That means that, for example, it's calculating the number of samples that will fall within that category. So that's why the area of the ball or the circle is going to be larger in those cases. So we're utilizing 4 channels, but we're going to take a look at how many channels exist and how can we utilize different channels on the plot more effectively, and what are examples of not careful kind of usage of all of those channels in different plots that we see. So the plot that you see here is an example that the length channel is not used effectively. This is a plot that basically looks at the car nationality and then also different cars. And you're seeing that the issue here is that it creates these bar plots. And the notion of bar plot is that the length should encode some information. And here, if you're ordering, for example, different countries in different order, right? And you're ordering them, and the length of these bars is going to be taller or smaller, then technically that you're encoding some kind of bias or unnecessary bias in the model. So that's an issue with this example, that the length channel is used for this kind of visualization, but length is not an appropriate measure or channel to be used in this specific case. So now let's take a look at how we can make sure that the axes that we have, X and Y, are going to be properly used. This is an example from 2015 from Planned Parenthood, hearing that the issue was that Planned Parenthood was accused of selling aborted fetal tissue. And the issue was that they were showing two different phenomenon on the plot, and they were arguing that the number of cancer screenings dropped from around 2 million to 900,000 from 2006 to 2013. And they were saying that the number of abortion cases started from 289,000 cases to 327,000 cases. And the way that you're seeing the issue is being raised here, or the way that this plot is not an honest or ethical plot, is that they're putting those two lines on different axes. So what you're seeing is that although this value right here is way smaller than this value right here, and in the other case, the 2 million was higher than the 289,000 number of cases, they use different scale in the beginning and also in the end, so that those values are now changing. And visually, you would think that, oh, now the number of abortion cases is more than the cancer screening, which is kind of a misinformation using the plot. A better way to plot this was to just directly put all of those values on the same axis. So for example, here, there's all of these service counts that are on the same axis, not having a different axis for this line or a different scale for this other line, but putting all of them in the same axis, so you can see that, okay, yes, the number of abortion cases increased, the number of cancer screening has declined, but still there is far more cancer screening cases compared to abortion cases. If you want to show that, oh, there was an increase versus there was a decrease for cancer screening cases, you can also do this comparative study or comparative kind of plot and show that. So one of them had a decline below 0 and one of them had an increase. So that's about the scale. One other thing to note is that if you're plotting something and you're focusing on one small region of the plot, you don't need to plot your entire data. And you don't need to visualize the entire data. So this is a plot from the number of COVID cases in New Zealand. I think this is before Omicron wave. And the issue is that the argument that they were trying to kind of show was how many cases they had at the peak of the original kind of wave. But with this exact kind of plot that you're plotting everything on the x-axis, it's really hard to see that peak or like how many days you were on that peak. So in the other case, we would say that don't visualize everything, visualize only the part that you're interested in. So this is also something else that you can have in mind when you're using visualization as part of your EDA as well. This is a plot from White House about COVID cases. You see that they're showing, okay, there is a trend from in around December and what happened during the Christmas days. And the issue with this plot is that it's not using the entire axis on the y axis. So always you can set the limit of your x-axis and the y-axis, and then you can say that, okay, I want the limit of the x-axis to be from this value to this value, which is what we did in this case. And you can also say that I want to have the y limit of my y-axis to be, for example, in the range that captures most of the distribution in our data so that you can visually see the differences a little bit better. Okay, so this is something that to have in mind in terms of scaling x and y using the same scale, and also what to use for the limits of the x and y axes that you have. One more consideration is the color channel. Remember that in the plot that I showed you, there were 4 information channels. There was x and y, there was color, and there was area. So now let's see how we can encode the color in our visualization. So this is a visualization that if you don't have any color blindness condition, you would be able to read the letters or the number 74 in the center of this circle. But if I simulate this for you and then show you that, okay, if you have a certain kinds of color blindness, you won't be able to tell the differences. So these are accessibility issues that you need to always have in mind, and there are different color schemes that uses appropriate kind of coloring schemes so that we don't have these issues for people who have red-green color blindness and such. So I'm going to go back and show you what they are. On the left, you see the jet color map. Jet color map has a lot of issues that we're going to talk about. And one of the main issues that it has is with the red-green color blindness issue, that you won't be able to tell the differences that much, but it also has other issues that we'll take a look. On the right, you're seeing Viridis, which is kind of another enhanced version of Jet Color Map, which was created by Berkeley. And we're going to talk about what the differences are and why Viridis is a better color map. And actually, Matplotlib now uses Viridis color map as opposed to Jet, which was historically being used in MATLAB and also in Matplotlib. So let's take a look at the differences. So if you take a look at this plot specifically here, so you see that different color maps are being used. The top row uses Jet color map, and the second row uses, for example, the grayscale color map. And you can see that, for example, here, there is a nice transition between like the black color to the white color. And also there is a nice transition here. But if you color exactly the same pixel values using the Jet color map, what you're going to see is this kind of a tiered colorway that you would visually think that there are tiers or the actual distinction between those values, but there are actually no distinction between them. It's actually a very smooth transition from one value to next generally. The other issues is that it washes out some of the details. So for example, here you would see that all of these light area vertical bars that we see in the graph, we don't see them here with the Jet color map. So all of those details are washed out. There's also an issue that if comparing, for example, this medical X-ray image, that if a physician just looks at the grayscale medical image, they would be able to see the differences. And then there are also light areas that they should pay attention to, and they'll pay attention to those areas, obviously. But what's happening with this Jet color map is that it highlights regions that are not necessarily should be highlighted. So for example, here, you would see that there is like literally it's popping out to you as a red region that if you show this to a physician, they would basically quickly take a look at that area, which is not an area that should be important. And it's still here, it's also colored as white, but they can also at the same time figure that, for example, this area might be more important. So it's not going to highlight it as like something so eye-catchy as red that the Jet color map is doing in this case. Why Jet color map is so bad and why Viridis is good, it has to do with the concept of lightness. I'm not going to go into the details of what lightness means, but technically what lightness means is that it says that the color map should be perceptually uniform, meaning that if the lightness changes for a specific delta, for example, say from this value to this value, and I change, for example, the lightness in this range for the exact same delta. So think about these two as similar delta values. You're seeing, for example, here that the lightness starts from this point and then it goes all the way to this point. So there is a huge kind of value change between these two. But if I go ahead and map, for example, these 2 points, you see that the differences is almost flat. So there is no difference between them. So this is why we say that Jet color map is not perceptually uniform color map, as opposed to with the Viridis color map, you're seeing that obviously it's a straight line. So it should be perceptually uniform. Every delta that you see, the delta in the lightness is going to be exactly the same. So this is one issue. Why is it important? Why is this non-uniformity is important? It's because at the points that we have these crossings, those are the points that is going to create those tiers and immediately jump to the next tier and changes the colors unnecessarily. So that's part of the reason that's happening. But generally thinking about the color, we have to utilize color in an effective way. Remember when we were creating different plots, we were saying that we decide about the plots depending on the type of the variable that we have. We use color also intentionally. We would say that if we have a qualitative variable and we have categories to show, let's go ahead and use qualitative color schemes. So that, for example, here, when I'm showing Virginica and I'm showing Sentosa, I'm using different colors entirely, one blue and one red. But if I'm going to show intensities or quantitative values, I'm going to visualize it with a color scheme that can visualize magnitudes. So you see that the magnitude of blue is going to change from the outer part to the inner part, showing that the magnitude increases at the center. And actually, there are two types of ways that we can visualize magnitudes. We can use sequential magnitudes that basically, if you take a look at the sequence, it basically starts from a light color, like white color, and then it goes all the way to the most intense value in that color palette. Or you can use diverging scheme, meaning that if I want to make sure that I emphasize both ends of the extreme equally, and I want to emphasize, for example, the small values equal to the high values, in example of, for example, vaccination rates, high vaccination rate versus low vaccination rate, I will use divergent color map. I'll use high intensity of blue for one and high intensity of red for the case that there is not enough vaccination, and then I'll use basically a light color such as white in the middle so that I show that the vaccination is kind of in the middle in terms of the intensity. It's not so extreme on any of both ends. So think about sequential color map and also think about divergent color map when you're trying to kind of distinguish the differences as well. These are the color maps on Matplotlib, which basically has all of these things that we already talked about. If you have a qualitative variable that you want to show, you want to use qualitative color maps. So you can take a look at all of those color maps. Most of them should not have an issue with color blindness if you use them, and you should be able to distinguish between the different categories easily, even if you have color blindness. These are perceptually uniform sequential color maps. And you see Viridis is right here. So it's sequential. It goes from green to yellow. And then you'll see kind of perceptually uniform color map, which we discussed what that is. You can also see divergent color maps right here. So if you want to visualize or color quantities, but you want to emphasize differences, you would be able to also use these color schemes, obviously, and then just the normal sequential color map is here. So just know that there is a palette available to you on Matplotlib, and you can choose between different color maps and then be able to select the colors that you want to use in your visualizations. So the next thing that I want to talk about is markings, because some form of marking is easier for human to understand as opposed to others. Why did I bring the example of lengths at first? It's because lengths is the easiest for human to visually understand and compare. Then we go a little bit more complex. We would talk about slope. We would talk about angles. And then that's the second layer. And then we go a little bit deeper, talk about areas, talk about volume. So things are going to get more complex as you go down this down this list. And then the most complex is going to be color hues for a human to visually understand the differences. So let's practically take a look at what if length is actually in fact easier than the area to understand. So let's do a practice and figure out how much longer is the long bar in this example. I'll let you measure it for 30 seconds and then I'll move on to Slido. Okay, what do you say? 4 times larger, 5, 6. Let's see. It's 7 times larger, but majority were correct. 6 or 7, that's a reasonable number. Now let's do a practice with area. How much bigger is the big circle compared to a small circle? This is going to get challenging. Measure it for another 15 seconds. You have to do this, put it in different regions. All right, let's see. Oh, was there no response? Oh, sorry. I revealed the response, but now you know it's 7 times larger. But it was supposed to be not so trivial. But you get the point. Understanding the lengths is much easier than understanding the area. And I'm going to show you a few examples that this kind of complexity of perception is going to be really important. So here you're seeing that I'm utilizing, or we're utilizing the length. So it's easily, we can tell apart the delta between Thursday and Friday and be able to understand which one is larger. But if you're looking at, for example, understanding the angle using pie chart, things are going to get more complex. So it's not easy for us to understand which one of them is going to be larger and what's the delta in those cases. So that's why in Data 100, we don't really like pie charts. Area is complex. Remember that we were doing that practice with the circle. So you can see that here we have African countries by GDP. And from the plot or using the numbers, you would see that the South Africa GDP is twice the GDP of Algeria. But just looking at those areas, it's not easy to understand that. But if we were to plot it using the length, some notion of lengths using these scatter plots, we would be able to kind of tell apart that, okay, Algeria is halfway to South Africa, and then be able to tell the difference between them that way. For the very same reason that we're not comfortable with volume, we also don't like word clouds unless it's in a slide of questions that you might get in summaries. Otherwise, word clouds are also very complex to understand. One of the items that was in the lengths was having the lengths from the same baseline. If you jiggle the baseline, then it's really hard to understand the differences between different categories. So quickly looking at this, you see it's really hard to understand the delta between these two areas because we just jiggle the baseline, and it's really hard to understand. This is also another example. The baselines or all of these categories are placed on top of each other, but a better way of visualizing it was to just individually plot each one of them so that we can tell the differences between CO2 emissions of different countries. If we have a condition that we want to visualize, it's better to pair conditions together in a way that we can tell the differences. So this is an example of men versus women income ratios or incomes depending on different degrees that they have. And if you just take a look at the differences that you see on this plot, it's not really easy to understand the differences between them. If that's a condition that you want to take a look, just put that condition clearly on the plot so that you can visually see the differences between them and compare them together. This is an example of superposition. We plotted two things on the same plot together. If we were more creative and we were just concerned with how the income gap changes as the degrees do change, we might want to even go ahead and visualize the ratios as opposed to having two separate plots. So here you would basically see that generally the ratio stays the same for different degree objectives, and it's not going to differentiate that much. So I talked about superposition. There are cases that we might want to put conditions next to each other. That's called juxtaposition. So this is the case that we use juxtaposition to put multiple things together in different conditions so that we can visually see the differences between them. The last thing is context. If you're going to visualize a plot for publication, you have to provide enough context close to where things are happening. So for example, here, On the left, this is a plot that might be suitable for your EDA, that you have a legend, you know what's happening in your plot. But if you want to actually publish it, then you have to basically have more details close to all of the lines so that a reader can technically follow those legends as they're looking also at the trend. It needs to have axis labels, it needs to have title, and everything should be in one place. So we talked about a lot of things, but the takeaways are everything that we do depends on the context. Now you have the tools and you know two libraries that you can make different plots. You know that depending on the type of the variable, you can make different plots to show a distribution or to show the relationship between two variables. And then we also told you that all of the plots that you're making, they need to have title, they need to have axis labels, and they need to be really self-contained. And also the takeaway is that if you're going to move towards a publication-ready plot, you might need to make additional effort and use like different fancier versions of plotting so that the context is really conveyed in a more efficient way, again, in a publication-ready manner. With that, this is the wrap of visualization. We're going to come back next week and talk about a new chapter in Data 100. Thanks for coming.